This mini lecture is about transformers. What do I mean by transformer? Let's just, for fun, do a Google image search for transformers so we can see what some of them might look like. I'm just going to type in transformers. Let's do an, oh, not a video, image search. And of course, the first thing that pops up is not what I had in mind. Is not an electrical transformer, but rather, we've got our Autobots and our Decepticons. Optimus Prime here. We've got Bumblebee. In any case, I just thought that was interesting that when I Google search for transformers, the first thing that pops up is not an electrical transformer in the image search. Oh, this is cool. I don't know if any of you guys might be too young, but when I was a kid, Transformers were a thing. And one of the toys in a Happy Meal one time was a transformer that was a hamburger, and then it could transform into one of the transformer robots. In any case, let us look for electrical transformers just so we can see. This one right here, this is the kind of electrical transformer that you probably see, um, outside your homes, on the electrical wire posts near your house. These transformers are going to take, these are what we call step down transformers. They take that high voltage, low current that's running through the power lines above our houses and convert them to lower voltage, higher current for use in our homes. So these kind of cylindrical devices are those transformers that you see on the telephone poles or the electrical wire poles. What transformers do, our electrical transformers, is they transform voltages and current from one value to another. They can increase them or decrease them depending on the application. Now, transformers operate by Faraday's law. They rely on the fact that we've got alternating current coming in through wires that are wrapped around ends of a metal core. So here's a schematic of a typical transformer. We've got a metal core here. This is what we call the primary coil. Maybe we have voltage current coming in from a power plant. And we take that electricity, send it through the wire here that's wrapped around this end of my transformer. And the changing magnetic flux that you have on this coil is going to be the same as the changing magnetic flux on this coil. So you induce an EMF on both of these coils, but that changing magnetic flux is the same for both of these coils. So you can take the ratio of the input voltage to the ratio of the output induced voltage on this other side. And we'll find that that ratio is proportional to the ratio of the number of times you've wrapped that wire around for the primary and the number of times you've wrapped that wire around for the secondary coil or the output coil. So over here on the left, we might have electricity coming in from our power plant. That's going to be transformed from some voltage and current to some higher voltage, lower current through this transformer. And then that electricity is going to get sent out across our electrical lines to our home. And whenever it reaches our home, we have to transform it back down from high voltage to low current to lower voltage and higher current for use in our homes. And we use another transformer, a step down transformer, to do that. And we induce an EMF, which is proportional to the ratio of the number of times you've wrapped those coils around the transformer. And that current induced in the second coil is inversely proportional to the ratio of the turns. And so here we have some relationships for the ratios of the voltage in our primary and secondary coils, the number of turns of those coils, and the current. And we're going to take a look at how we derive these expressions. And then we're also going to solve a problem where we apply transformers and think about the power that we lose as we send electricity across power lines in the city.
Here is an example of a very simple transformer. You have a metal core. That's what I have here. I've got an iron core. On one side, it's wrapped with wires, and it's connected to a alternating current source. We're going to call this our primary coil because that's the one that's connected to an alternating current source. So this is the voltage of the primary. NP is the number of loops or coils wrapped around for my primary. And then we have the secondary coil on the other side here. We see that the number of times we've wrapped the loop around the other side of this core is different. So we're going to call N sub S the number of coils here for my secondary coil. And then the voltage on this side is going to be V sub S, my secondary voltage, okay, or the voltage of our secondary coil. And on this side, we're doing something with that voltage, right? We've connected it across our circuit with a resistor. All right, so this is our schematic of a transformer. Now, transformers work by Faraday's law, right? So we have the voltage of our primary equals minus the number of coils of the primary times the change in the magnetic flux on that side over delta T. And for our secondary coil, we've got the similar equation. The voltage of our secondary coil here, the voltage output by my secondary coil, equals minus the number of turns of that coil times delta change in magnetic flux of the secondary coil over the change in time. But what we have here is an alternating current source. So we're going to get a fluctuating current. When you get a fluctuating current, the magnetic field created by that current, because remember that wires carrying a current have a magnetic field associated with it. So if you're constantly fluctuating that current, you're also going to get a fluctuating magnetic field. So you've got this changing magnetic flux because of our fluctuating current from our alternating current source. So that changing current from our alternating current source will give us a change in magnetic flux, and that will induce an EMF. What is going to happen is the key that's happening here is that this changing magnetic flux for this coil is the same as the changing magnetic flux on our secondary coil. So in both of these equations, for the induced EMF that we get on both of these coils, our first one, the induced EMF minus MP, change in flux. Okay. For our secondary coil, the induced EMF is minus NS, change in flux. These changes in flux for both sides of my transformer here are going to be the same. So that's the key, that the change magnetic flux of my primary coil is going to equal the changing magnetic flux for our secondary coil. Let's see what happens when I take the ratio of Vs to Vp. I'm going to take the voltage output from my secondary coil divided by the voltage input from my primary coil. Okay, so that will equal my secondary. I've got minus Ns delta phi over delta T divided by minus Np delta phi over delta T. So we said that for both of these coils here in our transformer, delta phi is the same for both sides. Okay, so these will cancel on top and bottom. My positive and negative sign, well, we're dividing a negative by negative. That gets rid of those negatives. So we have this relationship that the voltage output for our secondary coil over the voltage input for my primary is just the ratio of the number of turns of my secondary coil to the number of turns of my primary coil. So we see in this relationship that V and N are directly proportional to each other, okay? So if you want to have a larger voltage output compared to your input voltage of your primary coil, all you have to do is increase the number of times you wrap the wire around on the other side of the transformer in order to get an increased voltage on the other side. Yep. It's just the ratio of the number of turns of those loops. Another key is that the power input to my primary coil, so power to the primary, is equal to the power output from the secondary coil. So the power put in is equal to the power you get out. So we've got a couple of different relationships for power, but let's use the current times voltage. So my primary input power will be the current of my primary times the voltage of my primary coil, and that has to equal the current output by my secondary coil times the voltage output by my secondary coil. So if I go ahead and rearrange this equation and solve for Vs over Vp like I did over here, I divide both sides by Vp, okay, and then I have Ip is equal to Is times Vs over Vp, and then divide both sides by Is. Okay, so now I see that Vs over Vp equals Ip over Is. Okay, so in this relationship, V and I are inversely proportional to each other. That means that if the voltage of my secondary coil goes up compared to the voltage of my primary coil, then the current drops on this side compared to the current over there. So if my voltage gets bumped up over here, my current goes down, okay? And that's what this relationship shows us here. So we have these two relationships for our transformer. Okay, we've got a relationship that shows the ratio of the voltages between my secondary and primary coils to the ratio of the number of turns of the loop. And I also have this relationship that shows the ratio of the voltages of my coils to the current that induced EMF generates. Whenever we talk about transformers, there are two types of transformers. One of them is called a step-up transformer. In a step-up transformer, you're taking the primary input voltage and you're increasing it for your secondary output voltage. For a step-down transformer, you're taking the primary input voltage and you're bumping it down so that the voltage is less for your output secondary coil. In this problem, we are going to think about why it is advantageous to use transformers when we're taking power, electricity, from power plants and sending them across power lines before they enter our homes. So here, we're going to have a generator at a utility company, and this generator is going to produce 100 amperes of current. I'm going to call this I1 equals 100 amperes of current. Well, my primary is 1, right? And it's producing this current at a voltage, V1, of 4,000 volts. The voltage is then stepped up in a step-up transformer and is stepped up to a voltage of 2.4 times 10 to the 5 volts by a transformer before being sent out on a high voltage transmission line across a city. We're going to assume that the resistance of our power lines, altogether the effective resistance of the power lines here is 30 ohms, and that our transformers are ideal. So that means we don't lose any power. That means that the power input over here equals the power output over here. We have to determine the percentage of power that we lose in the transmission lines themselves through this process. So that's part A. Determine the percent power lost across our wires as we're transporting that electricity to our homes. I'll call that across wires. All right. So in my diagram here, I've got my power plant as my primary coil. The power plant is supplying alternating current over here, my primary coil. We've got into a transformer, so my primary coil here. And through there, we've got this current and this potential. And then with the magic of our transformer, we're going to step up that voltage over on this side to 2.4 times 10 to the 5 volts in my secondary coil. And then it's this voltage that is going to have an associated current, and that electricity is what's going to go through our high voltage power lines to eventually get to your home. And when that power gets to your home, it has to go through a step down transformer to take that high voltage, low current electricity through those long distance power lines and transform them down back to a lower voltage, higher current. For the percent power lost across this wire, well, let's see, the power lost. That's going to equal, well, there's a whole bunch of different ways so we can write power, right? It's I times V, it's I squared R, it's V squared over R. But we're going to think about the power lost across this wire by thinking about the current through the wire squared times the resistance of that wire. All right, so in our step-up transformer, we step up the voltage. When we step up the voltage, we reduce the current. So we have to figure out what is this current that is flowing through those high voltage power lines, and then we can figure out the power lost. Okay, so to get what is the current that's flowing through our power lines, which is the current, that is the result of our step-up transformer here, we have to remember that the power of our primary coil of the transformer equals the power of our secondary coil. So P1 is equal to P2. For this power, we can think about current times voltage, IV. So I1 V1 is equal to I2 V2. If I solve this equation for I2, we just divide both sides by V2. Okay, divide both sides by V2. So then that leaves us with I2 is equal to I1 times V1 over V2. So this is going to equal, we've got our input current is 100 amperes times our input voltage, which was 4,000 volts, divided by our output voltage, which was 2.4 times 10 to the 5 volts. Okay, so that gives us the current that is going through our power lines here of 1.67 amperes. All right, so this is what I'm going to use up here in my equation for the power lost through our power lines. So that will equal I squared R, 1.67 amperes squared times the resistance of these wires, 30 ohms, and that equals a power lost across our power lines of 83.7 watts. So that's just the power lost. We're looking for the percentage of the power lost across our wire. So that implies that I need to know something about the input power as well. So our percent lost will equal our power lost divided by our power input times 100%, right? So our input power, that's going to be the input current times the input potential. So this P1 is going to equal I1 V1. So our input power was 100 amperes times 4,000 volts. And that's 4 times 10 to the 5 watts. Now here's the important thing to keep in mind. The input power equals the output power. So PI, or P1 here, of 4 times 10 to the 5 watts, equals the power output over here, 4 times 10 to the 5 watts. But this current is traveling across this wire with some resistance. So that wire is going to dissipate some of this power here. And this is the power that gets lost as that current is traveling across the wire, okay? So our percent power lost is only 83.7 watts compared to the 4 times 10 to the 5 watts. So we're not going to lose that much power actually when we take that voltage and step it up to a higher voltage and a lower current. All right, so our percent power lost across our wire is going to equal this 83.7 watts divided by our 4 times 10 to the 5 watts. So our watts cancel, and we're going to multiply it by 100% to get us a percentage. And that percentage is only 0.0209%. Okay, so when we take this input current, input voltage, and step it up in a step-up transformer, we increase the voltage, we lower the current that gets sent out across that power line, we end up only losing, by dissipation through the power line, only losing 0.0209% of the input power. That's really good. That's a reason why we use these transformers, to reduce the amount of power that gets lost as we're transporting that electricity between where it's generated and where it's being used. Now, for part B here, with our last part, we have to find what percentage of the original power would be lost in the transmission line if the voltage were not stepped up. So we're not doing any step up. So just like we did up here, the power that we would lose if we didn't step up that potential, then the power that we're transmitting across the power line is going to have a voltage of 4,000 volts. It's going to have a current of 100 amperes. So the power that we lose is still going to be I squared R. But we didn't step up our voltage, so we didn't step down our current. The current was still our 100 amperes coming from the power plant. We square it and we multiply it by our resistance of 30 ohms. That gives us a power that we lose of 3 times 10 to the 5 watts. Okay, so we are losing a lot of this power if we don't step up that voltage, which steps down our current. So if we found the percent lost in this case, our percent lost will equal P lost over P in times 100%. So that would equal 3 times 10 to the 5 watts divided by 4 times 10 to the 5 watts. That's 75%. We would lose 75% of our power then if we didn't do this process of stepping up the voltage and lowering the current before we send out that power across those high voltage power lines.